YouTube. Okay, we're waiting for YouTube. Waiting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. All right. It takes 30 seconds for YouTube to confirm the audio. All right. So this time I'm gonna do. This is going to be. I named this lecture quantum gravity. What is a graviton? Take two. So this time, hopefully, no one is going to enter the room. Maybe I'll mute. I'll deafen my headset. So if there's other people talking, they're not going to interfere. Let me get the whiteboard going. Let me close this side. Can I move? Yeah, I can move this. That's it. That's the minimum. Let me minimize. Okay, so let's create new. Okay, this is going to be paste. Okay, quantum gravity, graviton. And this is going to be, oh, it's take two, whatever. And let me move this. I guess like this, it's good enough. All right. So, quantum gravity. So, what is quantum gravity and what is a graviton? That's a good question. So until 2 days ago, I thought there's no quantum gravity, there's no need for quantum gravity, and there is no graviton. But as I have been, rethinking since I developed my own theory of gravity, and it actually fits Einstein's general relativity. Since then, I started, and because my theory of gravity involves a fabric, and it right away involves quantum mechanics, because in my theory of gravity, there is a fabric. The universe is filled completely with a fabric. That can you undeafen using my phone as a listener because I'm using you want me to undeafen? Why do you want me to undeafen? Okay. So yeah. So according to me, my theory of gravity, the universe is filled completely with a solid that Einstein called the fabric of space. I think maybe he called him the fabric of space time. I don't like space time. I made a separate video about that. I just call it the fabric of space. But Einstein spoke about how the fabric is bent, is curved. So I don't think that's a correct. I wouldn't say interpretation. It starts from the inverse direction. So Einstein's theory of gravity, known as general relativity, it actually comes from an experiment, a thought experiment. So we can always start over from the thought experiment, and the thought experiment dictates that space is not curved. Rather, you could say the geometry is curved, but space has to flow. Space must be spilling into gravity wells. And since this space is a fabric, then nothing can move through this fabric. This fabric needs to drag massive into massive particles, into gravity wells. So this fabric needs to be there. So if it's there and it's grabbing all hold to of the apple, right? The apple has to fall down to earth. So the apple needs to be embedded in this fabric in order for this fabric to be able to grab the apple and drag it down into earth. That means this fabric needs to always be flowing into earth, and for the apple to always be embedded in this fabric. So that is what is causing the apple to be dragged into the center of the earth. And the same goes for the moon. So there is a fabric that the moon is embedded in, and this fabric is always flowing into Earth. That is what's causing the moon to fall into Earth. But the moon is also moving in a trajectory um, tangential to Earth, so it ends up being in orbit. The same goes for all heavenly bodies, they are all in orbits around each other. But the force of gravity, the effect of gravity, is just a fabric in which all the objects are embedded and they're all getting dragged into particles that have mass. And mass is created by the Higgs mechanism. So usually they say the Higgs field. So as I'm introducing a unified field theory, so there's only one field. So everything, all of quantum mechanics, general relativity, everything has to be about this one and only field, the unified field. I didn't invent the word the unified field theory. That is actually what many people work on, and many have given up. And Einstein worked on it for most of the, as far as I know, 35 of his last years. That's all he was doing, and he got nowhere. Okay, so since there is this field, and it has to be a solid in order for it to hold on to the apple and the moon and the galaxies. So there's no room for particles to move through it. And if a particle moves through the solid, it shouldn't be limited by the speed of light. And also, we have quantum field theory that says that everything is a wave. There are no particles, there are only waves. Well, then, that fits my notion that since there is this solid, that nothing can move through it, well, except for waves. Waves can propagate through it. So, and that's quantum mechanics. So quantum mechanics comes out of general relativity. So Galileo could have already developed general relativity, from which he should have expected to see particle wave duality and quantum physics, quantum mechanics. All right, but this now today I'm going to talk about quantum gravity. Okay, so first of all, there is no issue. We already know there's been already experiments in which little particles, quantum particles, were shown to fall towards Earth just like an apple due to gravity. So already we know from experiments that gravity acts on quantum objects. Now, what we have not confirmed yet is that quantum particles actually that have a mass actually create a gravity field, and actually they drag in other objects towards them. That, as far as I know, we have not yet experimented with, but I expect it to be true. I mean, so okay. So how does gravity work in the quantum realm? So it works just the same. Let me maybe draw a little bit. So there's no difference between how the Earth pulls the moon. Well, the moon is a little smaller, and it's very far. So maybe let's do it a little bit in proportion. So the Earth is actually tiny, and it's even tinier. They're really very tiny in relation to each other. But the Earth and the moon. Let's talk about the Earth. The Earth is pulling the moon towards it, and in the same way, you could say that a neutron is pulling, let's say, an electron towards it from a gravitational point of view. But let's say a neutron, let's say, would pull in another neutron towards it. So let's say this neutron, right? Just like the Earth. So how does the Earth pull in the sun? How does the Earth pull in the apple? Why should the apple move towards the Earth? So all the time, because the Earth has a mass, it drags in the fabric. The very thing that we call space or a vacuum is actually a solid. We cannot see it. I know it's really confusing. We basically, you could say, we cannot interact with it. Yeah, but that's because whenever whenever we are stationary, it is stationary. And when we move, we become waves and we propagate through it as waves. I know it's difficult to believe, but everything says that what I just said is true. So, we could go through all the proofs that everyone agrees with. We can go through Maxwell that shows that light is a electromagnetic wave that propagates through something. We don't know what. So I'm saying, yeah, it propagates through the unified field because, as far as I'm concerned, there can only be, there is just one field. This one field seems to be it. It has identical properties. Like if, for example, it has the maximum speed of propagation of energy through this field is the speed of light, whether it's gravitational waves or it's any other wave like electromagnetic waves, or maybe there's other types of waves. But as far as I know, all the waves move through the fabric, the unified field, at the speed of light. This suggests that it's the same field. There's only one field in the entire universe. There's not two, and there's only room for one. If you say that the universe is filled with a field that is basically a solid and I cannot even move particles through it, then how can I have another field in it? It doesn't work out, and I don't need two fields. One field answers all the questions. Okay, so this field, the way it works, first of all, it's made out of particles because we know that waves move through it. In order for it to be able to have waves going through it, it's got to be made out of particles that have a mass, and there is like springs connecting this mesh, this matrix of weights and springs. It is there. We cannot feel it because when a particle tries to move through this field, it gets stuck. These particles are densely packed, so it's like a solid. So when a particle tries to move through them, it can't. It gets stuck and it instead becomes a wave, and it waves through this field the way waves work. So it would push forward this first line of defense. It would slap it, and these particles would move forward and condense or compress these springs, and so on. And you would get a compression wave traveling through the solid. Just the way we can envision any mechanical wave going through any medium. So that's the nature of reality. That is currently, according to my unified field theory, that is the only field that is out there. That is the field that Einstein described. That is the fabric the fabric of space, or fabric of space-time. But I explained why time should not be part of that discussion. All right. So there is a field. So this field is always collapsing into, it's always collapsing into a massive particle. So a particle, and there's no difference between how this neutron is going to be dragged into this neutron. Let's say for some reason this neutron is much heavier. A neutron can become much heavier because of Einstein's E equals mc squared. So if we can impart more and more and more energy into a neutron, it can become heavier. The energy when we compress a neutron, so it goes from big to small, so it gains density. So density goes up because density is equal to its mass divided by its volume. And as we compress it, its volume goes down. And as we compress it, internally, there's 3 quarks connected with three gluons. So I don't think anything happens to the quarks, but the gluons become more compressed. And we know the gluons are very special. We can stretch them and compress them basically as much as we want. As much as we stretch gluons, they just become replaced with a replacement meson. So any two quarks gluon is a meson. So if we stretch two quarks apart, their gluon finally splits in. The gluon finally splits, and you get a quark gluon quark and another quark gluon quark. And the more you stretch each of these, just the more mesons you're going to get. But when you compress a meson, when you compress a meson, you just increase its mass. Its energy, its potential energy grows and grows and grows. I think there's no limit. There seems to be no limit to how much its energy and therefore its mass can grow. So because of E equals mc squared, when you compress, when the potential energy of a gluon grows, its mass must grow because the speed of light remains constant. The speed of light remains constant because the speed of light is just the speed of propagation of energy of waves through the fabric of space. So that is always a constant. Okay, so when we compress a gluon, its mass must increase, and I don't see a limit. I don't think that we know that there is a limit to this. So, and at the end, this would become the center in a neutron star. This would easily become a black hole. And I started discussing this, but I never finished it. I need to have a separate discussion about how a black hole is formed. But this is not the time. We're not talking about a black hole. Let's just make this neutron much, much heavier than this neutron. Let's say a trillion. This time, this guy is a trillion times more massive than this guy, which is basically what would happen in a black hole. So the nearby neutron would have the center neutron could grow to an incredible mass, whereas the nearby neutron would not. It's not important. It's not the point. The point is that this neutron has an incredible mass, very high mass and energy, because its gluons, because it's been compressed and the gluons are supermassive. Now this is a normal neutron. So let's say the relationship between the apple and the Earth is the same as this neutron and this neutron. Anyway, so so why does the apple fall towards Earth? So actually, let's start from quantum gravity. How does what is mass, and why does mass cause gravity? Okay, so mass, we know from the Higgs mechanism, mass is just an interaction. Just this neutron or just the gluons inside the neutron are just interacting with the Higgs mechanism of our field, of our unified field, of the fabric of space. So, so a particle, if it interacts, for some reason, I don't know why, but some particles we know interact with the Higgs and others not. So a photon doesn't interact with the Higgs mechanism. But a gluon does, and a quark does. I think everything does, except for, they say, a photon, and I think maybe also a graviton. But we're going to come to a graviton. All right. So we have a neutron. So so let's talk separately now. Let's talk separately about what. Okay, the Higgs mechanism. And I'm not going to discuss the Higgs mechanism. I'm just going to start from Higgs. So, but we have a particle. We have a particle, and this particle is surrounded by the fabric of space, the unified field, and it's the same as these particles. It's some particle. I don't know what it is. I think it has a mass. They're interconnected with springs. Apparently, I don't know. I don't know much about it. But one thing I do know that this field it has the Higgs mechanism. So when it interacts with a neutron or with a gluon, and with quarks, so it interacts with a neutron. It imparts, because of the Higgs mechanism, this this neutron now has a mass. Once this neutron has a mass, it causes the fabric, the field, the unified field, to just collapse. The unified field just starts collapsing into, it just disappears. It just gets eaten, just disappears. Now, you could complain, how could it disappear? Well, you could complain why it appears where we see dark energy. So, in the intergalactic or in the what do you call it? Intercluster space or whatever, in the vast emptiness of space, we know that we have dark energy, and dark energy is theorized to be, again, space growing. It seems to be, everything indicates to be, um, Einstein's general field equations constant, the cosmological constant, and it seems to just create space out of nothing. Just space keeps getting created, and we think it's being created faster and faster, and it's causing the accelerating expansion of the universe, at least as far as distances between clusters. I think even clusters are going to be ripped apart. I don't know. I don't know what we know about it. Anyway, but this phenomenon of space coming into existence out of thin air, out of nowhere. So don't be surprised that you're going to get a phenomenon like gravity, which are the gravity phenomenon and the phenomenon of the expansion of the universe. Everybody agrees are gravity, or phenomenon of gravity. They are phenomenon of general relativity, of theory of gravity. So it's a very similar phenomenon, only gravity is the phenomenon of the collapse of the fabric of space, and dark energy is the phenomenon of the creation of the fabric of space, of these particles together with the interconnecting springs. The springs, I think, are there because of the speed of light. So we know that we can get a compression wave going through. Let's do it with the red. We know that we can get a compression wave going. That is light, or electromagnetic wave, or gravitational wave. So we know that a wave can go through these particles. And the only way we can mechanically explain a wave is if there are particles. I think they have a mass, because otherwise the speed of light would be infinite, would be instantaneous. So they need to have a mass, and they need, and the springs need to be between them in order for a compression wave to be available. Now, because these particles have a mass, by the way, this also explains dark matter. We should have a different discussion about that, but we can just say very quickly. So if you have a galaxy, let's do it in a different color. So if we have a galaxy, right, we know that at the outer rim of every galaxy, the stars are moving faster than Newton predicted. So there is unaccounted for matter that we call dark matter that seems to be imparting gravity or mass to the galaxy. And this is also true for a cluster of galaxies. So a cluster of galaxy has the same issue, that it rotates too fast. That we're looking at all the light sources in a galaxy, and we calculate the mass of the visible galaxy, and the mass is just not enough in order to allow the outer rim to rotate so fast. So we need matter. So I came up with a theory. Right? My theory is that we have this fabric. It's everywhere, but it has a mass that has never been accounted for in all of the science of physics. So, well, let's account for it. So there is this mass, and it gets dragged into massive particles. So it has a velocity. It actually has an acceleration, but it certainly has a velocity. And if you're talking about very large, like something very large, like a galaxy or a cluster, so that this even a small velocity with a great amount of particles, you need to account for special relativity, right? Is it special relativity? Yeah. That as the speed grows, because the gamma function, so I don't remember, I think uh, m relativistic is equal to something like, is it gamma times m at rest? Well, it's relativistic and rest. So this is RE, and oh, they're both RE? Oh my God, relativistic and rest. So this is RT, rest. So anyway, it grows. So as you have, as the mass moves faster relative to an observer, the relativistic mass grows. I think it's something like this. I'm sorry if I'm getting it wrong. Maybe it's divided by gamma. I don't know. Anyway, so what does this mean? This means that the mass grows as all these particles are gaining. They have a velocity as the fabric of space collapses into a massive particle or a massive sink or a gravity sink. These particles have a velocity, and the same goes on a galactic scale and an intergalactic and a cluster scale. That there's dark there's the fabric is flowing in. It's flowing in from outside, from above, from everywhere. So you could basically say that there is a halo. I would say there is more of it. There's more motion around the center of a galaxy or the center of a galactic's cluster. But altogether, we need to account for the fabric that seems to have a mass because the speed of light is not infinite. So the particles that make up the fabric need to have a mass. So, and maybe the springs also have a mass, but certainly something here has a mass. So this thing has its own mass, even though we can't perceive it. And Einstein didn't take it into account. Maxwell, no one, well, Maxwell doesn't have any mass. But even Einstein, I don't think Einstein, yeah, Einstein didn't take the fabric into account. He just said there is a fabric. He discussed features, geometric features of this. He didn't even discuss the motion, but this moves, and we can separately prove that this space has to move and get dragged in. There's many ways we can prove that space itself must get dragged into at any level, quantum or intergalactic. It has to collapse into particles with mass. So this is dark energy. Dark matter. So someone should look into this explanation. This could be someone's PhD. Good luck. This right. If I mean, if you can build a model, that would be nice. So what happens is that, right, space itself flows in from every direction into and through. It also flows in through, right, from the edges into the center. So actually, as it's flowing in, it's speeding up. So you should expect extra speed over here. So there's extra mass over here. So extra gravity. This is exactly where you need the extra gravity, close to the outer rim. So it could be a viable. I don't know. I'm just saying it could be a good candidate for dark matter. All right. So let's get back to quantum gravity and the graviton. I don't know if we'll get to the graviton, but quantum gravity, I think it's a little bit straightforward. Anyway, so quantum gravity. So you have the particles that make up the fabric of space, and for some, and they interact with, let's say, a neutron, and because they interact with the neutron through the Higgs mechanism, they impart mass to the particle. Once they impart mass to the particle, well, then the particle starts interacting with these masses because there is masses here. So it starts pulling them in. So space itself gets dragged in because it has a mass and because the neutron has a mass. No, that can't be it. No. It causes a collapse. Maybe the vibrations, because we know that the Higgs mechanism is just a very high vibration, again, because of E equals mc squared. Is it? Because of the high vibration, there's high energy, and that's the mass? Maybe. Anyway, but we know that the Higgs mechanism is just a vibration. So this particle just vibrates, and maybe it breaks down because of this vibration. It just breaks down these bonds, and the nearby fabric just falls apart and collapses. It falls apart and it gets swollen by the neutron. And it doesn't matter for how long. For the rest of time, this neutron is going to be engulfing endless amounts of space, of this fabric. The neutron is never going to be full. It's never going to be satiated by drinking all the space that's available. By the way, this is three-dimensional, so it's swallowing space from all three dimensions. Okay, so that's it. Okay. So space itself is moving in now. Space itself is a solid. So if there is a particle over here, it doesn't matter what it is. Let's say it's an electron. I don't care what it is. Any particle must be embedded in space because space is a solid. So guess what's going to happen to this particle? It's going to get dragged in because this thing is just it's falling apart, it's getting eaten up. This thing is just swallowing, it's dragging in from every direction the fabric of space with everything that is embedded in it, and things are embedded in it. So the moon is embedded in space, the earth is embedded, we're embedded in space, and the earth made out of neutrons and protons and electrons, and so those interact with the Higgs mechanism, so they have masses, so they cause the collapse of the fabric. So the fabric gets dragged in and we get dragged in. And we call this gravity, and it feels like a force. Yeah, but the force is because the ground blocks us from getting swallowed by this field, by this drag. So the drag is acting one way, but the earth is pushing us up. When we feel the force pushing up, but the force pushing down, you can call it a force. That's the interaction. That's our interaction with the fabric that is getting dragged through us. So you can imagine like a rain or some water. Imagine you're sitting inside a vacuum. Let's move this up a little bit. So imagine you're sitting inside a vacuum pipe. It's connected to a vacuum hose. It's connected to a vacuum machine. So you have a vacuum machine over here, and you're sitting right here, and you're getting sucked in. Now, you would feel tremendous winds sucking you in. You don't feel the winds because the winds are flowing through you, through every particle and the internals. Every electron is feeling this wind. Every little particle is feeling this wind going through it. So but it's suction. It's just suction. You're just getting sucked in, and that's how you should feel. That's how you should imagine it. Just that you're standing on. Imagine there is something that you're standing on that's just not letting you fall in, but you can feel. So you interpret this sucking as a force. Okay, you can interpret it as a force. Certainly, at the end of the day, there is a force pushing you up. So you could say that there is a force. So the way Einstein said, he said it's just the geometry. No, it's not the geometry. The geometry, you could say, is the curvature, and that is what is telling space to flow. It's a way to describe the direction and the flow of space. But space must be flowing. How do I know space must be flowing? So we can go to Einstein's thought experiment. Jimbo, if you can move your thing here. Anyway, so if we imagine Einstein's thought experiment in the elevator slash rocket. So Einstein said, can you move it away? So Einstein said, thank you. You turn it on? Okay. So Einstein said you cannot tell the difference if you're standing in a rocket or you're standing on Earth. Okay. But part of the experiment says that you're holding on to a ball. Let me expand that. You're holding on to a ball and you're letting it go. So you're holding on to it and then you let it go as the ship is accelerating and you see the ball falling down. But you know, right, that just before you turn the engines on, you let go of the ball, it didn't go anywhere. Okay, but now that the ship's engines are running, nothing has changed. You let the ball go and you see the ball as if it's falling down, but you know the ball is not falling down. You know rather the ship is accelerating, it's moving upwards into space, which means this this ball is stationary. But you know that you're moving through space. You know it, you must be moving through space. You have to decide someone is moving through something. So if you let go of the ball, you see the ball accelerating downwards. So, okay, if you're in the ship, you know you're accelerating through space. But what if you're on Earth and you drop the ball and you see the ball falling? You still have to assume you're accelerating, you're moving through space. And that's how I know space must be flowing, because Einstein said so. He didn't say so, I think he didn't get it right. I'm following Einstein's thought experiment. He said something about curvature. There's nothing here about curvature. If you fire the laser, you would see the laser curving. That has nothing to do with it. That's not curvature. That's the light beam curving. Has nothing. Curve is not. Space is not curving. It's not happening. Space is necessarily flowing through you. It has to be. If you assume that there is space, you're moving through it, right? Look, you have to decide. So you must be moving through space, which means because of the equivalence principle, you cannot tell the difference. Are you in a rocket or are you in Earth in the same box? You don't know where you are. You let go of the ball. The ball appears to be falling down. You have to assume that space is flowing through you, because you have to assume it's on, right. It's the equivalence principle. You might as well be accelerating through space. You have to imagine you might as well be accelerating through space and space is flowing through you. That's how I know space must be moving through me as I'm sitting on Earth, which means, again, going back to quantum gravity, there's just particles. The Earth is just many, 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 many particles. Some of them are neutrons, some of them are protons, very similar, both 3 quarks and 3 gluons. That's most of the gravity of Earth. So I have to assume that whatever is dragging down space, that's it. It's the neutron slash proton. It's the gluons and the quarks that must be dragging in space. It has to be that way. Space is dragged in. Nothing to do with curvature. Curvature doesn't explain why the laser beam curves. It doesn't explain it. Nothing. So, right? So, if you assume that you're moving through space and you fired the laser beam, so as you moved up, the laser beam with its inertia, assuming a laser beam has inertia, so the laser beam, the original laser beam is still the original particle that you fired initially, is going to hit a lower place than where you are now. That's fine. That it so a laser beam light seems to bend. Don't let that confuse you with the notion that space is curved or space is bent. That's complete misunderstanding. Nothing to do with it. I don't know. I think that this is where the misunderstanding comes from. Space is flowing through into massive particles. If a light particle is here, it's going to get dragged down. But since it's moving so fast to the left, we're only going to notice a tiny drop and a tiny, tiny, tiny. It looks like it's curving. Fine, that has nothing to do with it. Space must be flowing through and dragging light particles that have no mass. That's the way it must be. That's where I got the notion of the fabric directly from this experiment. So there must be a fabric running through us. It must be raining through us. This is evidence, since general relativity is completely based on this thought experiment. Then my interpretation must be correct, and Einstein's interpretation of curved space is incorrect. Space is not curved. You could say, I don't even say that anymore. The geometry is curved. I don't need it. I don't need to say the geometry is curved. Space flows into massive objects. Done. There's no. It's very simple. So, and everything works now. Oh, because we magnified the picture. Okay, so where were we? Okay, so back to quantum gravity. So here is our neutron, and we explained everything, I think. That's the way it works. It's just that the fabric collapses into this thing. Now you're going to argue, let's look at the universe, because you're going to get a paradox. If you just assume that you have a universe and you have galaxies or clusters of galaxies, so ultimately space is getting sucked in. But if space is getting sucked in, where is space coming from? So either all of space is right. This is going on for trillions of years. Oh my God, billions of years, like 13 point something billion years. It's going on. That space is getting dragged into massive objects. Theoretically, maybe it should have run out. Like space should have run out, and so either it should cause the shrinking, just the mere fact of the mechanism that I just described, it should actually cause the shrinking of space itself. I'm not even talking about due to gravity things should no. But let's say the centrifugal force is pulling everything apart, so it's stable, but just because something is sucking out, all everything inside is sucking out the fabric of space, and it's not getting replaced. It's just collapsing, 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 collapsing. Everything, the fabric of space is collapsing. This liquid solid is collapsing into all the stars and all the black holes, in all into all the matter in the universe. It should certainly cause a shrinkage of the universe, but it doesn't. And this is where dark energy comes from. So dark energy is someone is like pouring in the fabric into the vacuum or the um, cluster, into the intercluster or the intergalactic space. Someone is pouring in and replenishing the supply, and that is dark energy. I don't know where it's coming from, but in my imagination, I'm imagining the particles that make up the fabric of space, and once in a while a new particle shows up with all the connections to its nearby particles. So new particles for some reason are coming into existence. Okay, so we know that the zero energy cannot be zero. We know this because of the Heisenberg uncertainty. So I don't know where Heisenberg uncertainty comes from, but I think it comes from the zero energy of the fabric. So we know that particles are always coming in and out of existence. This suggests that these particles are always vibrating and they can never rest. At zero energy, they are vibrating. So we're always getting Heisenberg uncertainty, and we're always getting particles coming in and out of existence, waves coming in and out. And maybe, I don't know, maybe that creates, just because of that, but on average, I don't know. I didn't think about it. So I don't know. Okay. So how long have we been? We've been going for 45 minutes. All right. Not so bad. So we discussed quantum gravity. Now, quantum gravity, actually, I don't think I didn't. I thought about what do you call it, the graviton. It doesn't really have anything to do with the graviton, but I can still maybe. I think did I say enough? Maybe I should say a little bit about a black hole. I think I had a separate lecture about a black hole, but we can discuss how I've discussed it. I can rediscuss it. How a neutron star becomes a black hole. So at the center of every neutron star, you have a neutron. That neutron is experiencing a growth in mass because it's just under more and more and more pressure. And this is just causing the fabric of space to flow in. So in the beginning, it has a normal mass, but its mass keeps growing and growing and growing, and it keeps shrinking. As it's shrinking, its mass keeps growing and growing. Its density keeps going up and up and up. And then you get to the point where the density is the density of a black hole. Do I have the equation? It's very easy to figure out the equation of a black hole. It's the Schwarzschild. We don't need Schwarzschild. I have a separate lecture how to develop Schwarzschild radius directly from Newton, which can be developed directly from Galileo. Everything comes out of Galileo. We don't need anything more than Galileo, which is basically what Einstein did. Einstein went back to Galileo and started from scratch to develop general relativity. So the density goes up and up and up. And so until as the density goes up, well, you don't even need the density to go up. All you need to say that I mean, the volume keeps going down in order for the gluons to keep getting compressed more and more. But fine, the volume goes down and down, but this causes the compression, which causes the potential energy and the mass, and because the energy goes up, the mass goes up. So this causes the density to go up. Fine, whatever. But as this keeps going up and up and up and up, well, as the mass, it's enough to say as the mass keeps growing, so the fabric just keeps flowing faster and faster. The fabric keeps flowing faster and faster. At one point, the fabric is going to be flowing into the neutron at the speed of light. All right. And remember, this is just a fabric. So light, if it wants to travel, it has to travel as a wave. Let's say it wants to leave, it has to travel as a wave propagating in this direction. But guess what? If the flow, right, this is the flow, if the flow of space inwards is as fast as the flow of propagation of waves through the fabric, we have achieved a black hole. Light can no longer escape this region. So at one point, we're going to develop the neutron's radius will become an event horizon, and later on it will just keep growing and growing. And as soon as it starts growing, you get another effect. This space becomes infinite, right? Because imagine you're here. If you're here and right, if you want to travel this way, it takes infinite time because you cannot travel faster than light. And space is flowing. And by the way, space is not limited. The flow of space is not limited by the speed of light. Space can flow in at any rate, at infinite rate. This can keep growing and growing and growing infinitely. There's no limit to how fast space can flow. And as soon as it hits the gluon, it breaks up and disappears. I don't know how exactly that happens, but so it just flows in faster and faster. So the distance, if you want to go that way, is infinite. The distance this way is very short. But imagine you're very close to the event horizon. Yeah, the distance towards this is very short always. It's very fast to go and hit and get smacked by the gluon, which at one point is going to be super super heavy. So smacking against it is going to be very painful. Um, but um, but certainly going outwards, you experience an infinite distance because you can travel forever outwards. So you're basically in free fall. Yeah, it's a little bit problematic because this way, it's if you don't try and travel that way, if you go into free fall, you immediately die. So it's one way infinite. It's infinite as far as right since we're constrained to travel through as waves through the fabric. We cannot travel faster than the speed of light. So we're trapped. And okay, anyway, but that's quantum. That's another right. Everybody says, oh, you cannot understand quantum gravity. General relativity doesn't work in the quantum realm. I never understood for the life of me, I never understood that statement. Every time I looked into it, I never understood it. And today, not only do I not understand it, I have a complete, not complete, but I'm beginning to build a complete, but certainly my explanation, I feel, is much more complete than any explanation I've ever heard from anyone. I've never heard such a complete explanation about I'm putting together so many puzzle pieces. So I never had an issue with quantum gravity, but there you go. Here is a theory of quantum gravity. I don't have an issue with it. There's nothing surprising about it. There's nothing that you could say, oh, that's anti science. The fact that the fabric disappears when it impacts a gluon or a quark, talk to the dark energy where a lot more is getting inserted out of thin air into into the middle of nowhere, out of nowhere. At least here, something is causing the destruction. So I don't think this does not seem to be a violation of known science. Okay, so that's a quantum gravity for a black hole, quantum gravity for a neutron, for Earth. Very good. Okay, last thing I wanted to discuss is the graviton. All right, what is the graviton? Good question. I don't know, but I'll tell you what I do know. I don't know how to discover it. I don't know. I'll tell you what I do know. All right, so let's talk about Maxwell's equation. So according to Maxwell, electromagnetic theory. So if you have an electron, here's an electron. If you have an electron and you are able to move it a little bit, so according to Maxwell, you don't need to move it by a photon. There is no, Maxwell doesn't account for uh, quantum mechanics. Neither does Einstein. Einstein doesn't have quantum mechanics, and neither does Maxwell. You should be able to derive, from what I understand, Maxwell from Einstein, from the Einstein's field equations of general relativity. Anyway, let's assume we're taking an electron and we're just moving it a little bit up. So we would have to grab it somehow, which obviously is impossible. I don't think it's possible to grab it. So it's just gonna be a thought experiment. But this works in Maxwell. It's not even a thought experiment. You should be able to run a simulation in a computer program that lets you run a simulation of Maxwell's equations, which should be doable. There should be free software. By the way, general relativity and everything I discussed, no, no. But okay, anyway, you should be able to run a simulation of what I'm about to say. Okay, so you take an electron, you just move it up. That means you'd have to grab it, accelerate it, and then decelerate it to here. Okay, what effect would this have on the universe? So according to Maxwell, you're literally going to shock the universe. So according to Maxwell, when you move, right, this is the electron. We moved it from here to here. So before you moved it, it was emanating just an electric field. And after you moved it, of course, the new electric field is here. But in the interim, the electric field was moving. Now, this effect, let's assume you did it very quickly. You just grabbed it, moved it, and stopped it. So this changed. Let's say we have an electron here, a detector. This detector is just an electron. Let's say we have an electron here. So according to Maxwell's equations, or Maxwell's electromagnetic theory of electrostatics and magnetism, electromagnetism, basically it's going to take the speed of light until this electron will notice it. So in the beginning, this electron was getting repelled. It was feeling a force that way. Let's say we had it tethered. So it's a test particle. It's tethered. We place it wherever we want and we feel it. So in the beginning, it felt a force going that way. And after, at the end, it felt a force going this way. So the force changed. The direction changed. But this didn't happen instantaneously. So it happened with the speed of light. And not only did this particle notice this difference, actually all over the universe, the entire universe now, with the speed of light, there is a shock wave, there's a bubble, a three-dimensional bubble. I'm gonna have to create a new page. So let me create a new page. There's no way to do a second page, right? We need to just create a new one. All right, so we're almost done. So this is the second page of quantum gravity. No, gravity. Okay. All right. So, all right. So what are we gonna do? So we said that we're moving the electron. So when we move the electron, we're creating a shock wave of information. Right? There is an information. If we have many test particles, right, we can also imagine an electromagnetic field. So whatever information is being delivered, it's being delivered as a sphere. These are spheres. These are not circles. These are three-dimensional spheres that you can imagine an electron, a test particle, that is noticing this change. And this goes on to infinity. To infinity, to the entire visible universe. The entire visible universe is going to feel this tiny vibration, tiny motion of the electron. Okay, so but quantum mechanics says that if you have a detector, if you actually have an electron here, right, you have many electrons everywhere. Actually, if this amount of energy, let's talk about the amount of energy the kick that we gave this electron. So let's say, now let's talk about, let's leave Maxwell alone, or let's take Maxwell and add quantum mechanics into Maxwell, which basically no one does. They don't talk about Maxwell and add relativity to it. They have these weird diagrams. I don't like it. I take the original simulation, which hardly anyone displays, which is a terrible thing in of itself. But okay, we're starting from, and by the way, this is just one wave. This is not multiple waves. Don't think of these as we only created one wave. We just shocked the system once. And that's it. There's no more shocks to the system. So it's one wave traveling through time. This is at t equals 0. This is T1 and T2. Let's say every second we measured and we saw, and and here comes the problem. So let's say we only imparted on this electron the minimal energy that we can impart to an electron, which from quantum mechanics, that is the amount known as, I think that's a photon. The minimal energy you can impart to an electron is a photon. It has to do with Planck's constant. I'm not exactly sure how to play with Planck. I didn't go through this too much yet. So we gave the system the most. We added the most minimal energy that we could to this electron, and it actually gave it away. So we imparted this minimal energy, but then we took it away. It went away through this wave. Now this wave coming out has the minimal energy possible in the universe. This is the smallest this is where the word quantum comes from. This is the smallest amount of energy to exist in the universe. But this wave, it should be big enough to go from it should be able to go all over the visible universe. However, according to quantum mechanics, the first detector to interact with it is going to destroy the entire wave. So it's not really a wave, it's something else. It cannot. Look, I don't know, I still don't know what it is, right? So according to my theory, so what we have here is a fabric, the same fabric, the unified field, and this sphere of a shock wave. By the way, it's an electric wave and a magnetic wave, and they're interacting, and they're going through this fabric, just as Maxwell. This is exactly as Maxwell described. It's just that it happens through the unified field. It always happens through the same field from the gravitational field. The gravitational field is gravity is the dragging. It's two different actions. The dragging, the actual motion of this field is gravity, but just a wave going through is electric. But it's not any wave. A gravitational wave looks different than an magnetic wave. It's different. But some people are going to yell and going to say, oh, so you think you're one of those conspiracy theorists like the flat earthers. They say that gravity is actually an electromagnetic wave. I'm not saying that. No. I'm following everyone to the T. I'm just explaining. I'm putting the puzzle pieces together. So I'm using Maxwell, but I'm also throwing in quantum mechanics into Maxwell. I'm not the first one to do it, I hope. Anyway, so according to quantum mechanics, the first interaction we have with this wave. So let's say we're on Earth, and this was some explosion a few billion years ago, and right now on Earth we're detecting this wave. So if this wave is of minimal energy, according to Planck, then our interaction with it should cause it to collapse. So if simultaneously it was interacting with another electron at the other side of the universe, only one of us is going to notice this specific photon, right? Because we imparted the photon, the amount of energy we impregnated this electron with is the energy of a photon, but then the energy of a photon came out of the system. So we gave it energy, but then we also stopped it. So did we really? Yeah, we do work? Yeah, I think we didn't do work. So where's this energy coming from? So we pushed it over a distance and then we stopped it. Yeah, I think we did work. We accelerated, but then we decelerated. So we didn't do any work. Wait a minute. We took the electron. There's no resistance because There's no gravitational field. We accelerated it. So we did energy. We invested work. So we invested energy. But then we decelerated it and got all the energy back. So where is the energy of this wave coming from? But if we did this many times, we're always getting the energy back. Are you going to say that we're not doing any work? If I push something and then I take away its energy and it stops, yeah, it's peculiar. So I don't think it's possible. So if I have mass and I'm just gonna take it and move it up and down, 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 I'm not doing any work. I can do this forever. How could that be? How can I move this up and down forever and create as many and shock the universe without expanding any energy? I'm not expanding energy. So why is any energy coming out? Why are you saying unless you say that when I move it I must be losing energy because I'm moving it through the electromagnetic field, through the fabric. So according to my theory, right? So okay, but this is Maxwell's too. So Maxwell says there is a field here, and you are imparting energy into the field. So you're losing energy. You are creating yeah, okay. So if this was a mass, we'd be right. If this was a neutral piece of mass and we were moving it up and down, yeah. So we're not investing any energy, we're investing pushing it up. We're then getting back when it's pushing us up. Right? So imagine a spring. We just have an arm and a spring, and we're just moving up and down forever. If the system is frictionless, this should go on forever. But because Maxwell said this is an electron, so it's negatively charged, and we have the fabric to worry about, we're shocking the fabric. Okay, so that's good. So when we move the electron through the fabric, we're creating electromagnetic waves. That's fine. Okay, so we're following Maxwell. We're creating just one motion. So we're creating an electromagnetic wave, but it's the minimal motion that we could move an electron by. It's just a single photon. It's the smallest. It's an H. It's a Planck. Sorry, it's a Planck. It's a Planck energy. It's the minimal energy possible in the universe. That's the energy we invested, and that entire energy went into shaking, causing a disturbance in the fabric, in the unified field, or in the electromagnetic field, which are all names for the same thing. There's only one fabric. So now there is a wave, right? It's waving. We cause this thing to wave, and this wave is traveling. A single wave is traveling. But what's bizarre about quantum mechanics is only one. If this is that minimal energy, and we have an electron in our detector here, and an electron in our detector here, only one of them is going to hear or is going to detect this energy. So if this one gets it, this one will not. However, these could be a distance of 100 billion light years or whatever. The width of the universe is almost 100 billion light years. So this suggests, of course, according to quantum mechanics, that the information is moving faster than light, but there's no information moving between them. So we're not violating the speed of. There's no violation here of any known physics. Of course, I'm going to be the first. I'm going to be the last one to disagree with consensus physics. I'm not disagreeing with any consensus physics. I'm just everybody agrees that according to quantum mechanics, these two. They would say maybe that these two electrons are entangled, and or something like that, or this photon, whatever. But there seems to be now a communication at infinite speed, because we know from laboratory tests that as soon as this electron detects the photon, detects this energy, definitely this one will not. And if this one does, definitely this one will not. Only one of them will detect it. So And this is a repeated experiment. This is the electro. This is Einstein's Nobel Prize. This is the photoelectric effect. This is Einstein's paper on photoelectric effect or something like that. I mean, this is my interpretation, but no, this is not. No, this is not. No. This is just the collapse, what they call the collapse of the wave function. That there is, you could argue that this is a wave, and as soon as we detect it, it collapses. I don't know if that's Schrodinger's wave function. I don't know. Is it? Maybe my interpretation of Schrodinger. I don't know. It's just my interpretation. This is just Maxwell with quantum effects. But what we do know is that only one of them only one electron can ever detect this energy. Okay, that's given. That's a given. And where's the photon, by the way? Right? We never saw a photon. Notice that in this very realistic discussion, there's no photon. There is no photon. There's no particle in this discussion. This discussion actually is very reminiscent of quantum field theory, that everything is a field. But where's the photon? Where's the particle? Where's light as a particle? So there is no light as a particle, as far as I can tell. The only interaction that we can say there is a particle is when we could only impart a quantum amount of energy on the electron. We call it a photon. We say that we imparted a photon, but I don't think there is a photon. And the next time is when our detector detected a photon. It didn't detect a photon, it detected an electromagnetic wave. It didn't detect a photon. The fact that we detected, we call a photon. I don't think we see photons. All we get is a detection, and we just call it. It behaves in a certain way that we call a photon. We never see I don't think we ever see a photon. In this sort of accurate Maxwell plus, this is Maxwell with quantum effects. So we don't see a photon. All right, but that is all I wanted to say. Now let's talk about the graviton. Graviton is going to be very similar. Very similar. Okay, first time. Actually, everything I introduced to you up till now is my first time introducing it. So I'm sorry for being so slow and lengthy. I'm still thinking. This is still work in progress. This is just 3 or 4 days old, this theory. So, and I'm barely spending time analyzing it. It's just here and there. All right, what is a graviton? So a graviton should be very similar. So we're going to take a particle with mass, and we already said like a neutron or even a gluon, but we can't separate a gluon, not even a quark. A quark and a gluon and a quark, yeah, but let's just take a neutron. So here we have a neutron, and we already said it's interacting with the field, with our unified field, and that is this interaction causes it to bounce back and forth. The interaction is the bouncing back and forth, and this bouncing back and forth, that is the mass. That is what seems to us as the mass. Okay. Why is that? I think it's because, well, if it's moving back and forth very quickly, then it can't move through distances at the speed of light. It has to move very slow. The more it bounces back and forth, the slower it has to move through actual space. That's what we call mass, basically, because it's moving at the speed of light. It's interacting with the Higgs mechanism at the speed of light. This bouncing back and forth is always at the speed of light. It's a wave. It's waving through the fabric at the speed of light. But this, because it's waving at the speed of light, it cannot progress at the speed of light. It cannot move as a wave, like a photon, like an electromagnetic wave. It cannot move at the speed of light because a lot of the speed is already taken up by moving back and forth. So if you keep running and back, running back, running, you keep running forwards, backwards, and every time you move forwards just a little bit. So of course you cannot move at your speed. Your speed, let's say, is c. If you move at c, but you keep moving back and forth, and every time only a little bit forward, so well, you're moving slower, much slower than the speed than your original speed c. All right, so but that's the Higgs mechanism. I still know very little about it. Anyway, so because of the Higgs interaction, this particle now has a mass. Because it has a mass, so we start getting the collapse of the fabric into the fabric starts flowing into this neutron with the mass. By the way, the flow in doesn't seem to increase the mass. I don't think it causes the increase of the mass of the neutron. So every particle seems to have a mass. Every particle of the fabric seems to have a mass, because otherwise we wouldn't, I don't think we would get the speed of light. We wouldn't be limited. We would have infinite speed of light. So these particles are falling in. Where were we? So what happens to the mass? So this neutron is not going to grow in mass because it's just out there experiencing, endowing gravity to the gravitational field. I mean, it's dragging in space, but it's not growing in mass. I mean, we know that neutron don't grow in mass over their lifetime. So I don't know what happened. They seem to be, so this particle and the surrounding spring seem to just disappear on impact, just like they appear out of nowhere in the dark energy mechanism. Okay, it shouldn't be surprising. It's not a violation of known physics. We know physics to be doing this, as far as we know. Okay, we're almost done. We're almost done. How long have we been? Okay, an hour and 17 minutes. We're almost done. All right, so let's do the same now to create a graviton. The same as we did up here to create a photon. Notice we never created a photon, but we noticed a photon by definition. This is this interaction that the detector detected a wave of minimal energy. We just call it a photon. I don't think we ever see photons. As far as I know, we never see photons. But we see a quantum mechanical effect of the collapse of the wave function, of the collapse of something. This, what I call it, I don't say the collapse of the wave function. I just say there's a collapse of the bubble. This is a bubble. It's a three-dimensional wavefront, and as soon as it interacts with anything, that's it. All the energy is gone. It had to give away all its energy, and poof, the whole thing is gone. Even though this is the size of the known universe, it's instantaneously gone. So just before, if it was supposed to interact with this electron at the same time, only one of them is going to accomplish this, because this interaction is instantaneous, and we know this happens. This is known physics. This is quantum mechanics. And I think this is spooky action at a distance from Einstein or EPR. Anyway, okay, we know there is spooky action at a distance. I'm not inventing that. All right, let's go back to gravitons, our final topic of the day. All right, so a graviton is going to be very similar. We're going to take our neutron, and we're just going to move it. We're going to drag it through the fabric. Remember, we're surrounded. Maybe let's use this blue. Is it blue or purple? I don't know. I think it's blue. So this is our fabric. Many dots. This is our fabric. So we're moving through a fabric. But remember that the fabric is being dragged in. The difference between the way electromagnetism works, it's a wave, it's a propagation of energy through the fabric. It's a propagation through, well, A gravitational wave is going to be also a propagation through, but this is a little bit different because as the electron moved up, it's actually going to cause yeah, you can look at Maxwell exactly how it works. Really it's not like a sound wave, which is a pressure wave. An electron does not cause a pressure wave, or at least not. It's not transversal. It doesn't go in and out of the direction of the propagation. So if the propagation is that way, okay, let's try that again. If the propagation of energy is that way, okay, so don't think of the wave as a pressure wave moving right and left on the trajectory. Rather, the electro part of the electromagnetic wave is actually going to move in and out. It's going to move in and out of the screen relative to the propagation. And the magnetic is going to move right and left relative to the propagation, but it's not going to move along the propagation. The motion along the propagation is actually going to be a gravitational wave, not gravity. Gravity is just the dragging it's just the motion. So these are different effects. So gravity is the flow of space. Gravitational wave is going to be it's going to be a pressure wave, very similar to sound. Sound wave and a gravitational wave are very similar. The compression is going to be transverse. It's going to be with the direction, with the vector. If you look at this arrow that I drew and think of it as a vector, so gravitational wave is going to be along this vector. So if we need to draw the magnetic is going to be, let's draw an X. That's the way we draw it. It's going to be into the board or into the screen. Let's see, because of the right hand rule, I think it's, so if this is the direction of propagation, I don't know. It's either in or in and out. It's going to be in and out. So it's going to be in and out. The wave is going to be waving in and out. The electro part, the electric wave is going to be moving in and out, whereas the magnetic is going to be right and left, which is really bizarre. It means that the arrows, that it's going to move the fabric to the right as it moves through, and then to the left as it moves through. It's really weird, and these two are going to be in tandem. They seem to support each other as they propagate each other, as explained by Maxwell. I'm not saying anything new. I'm just explaining to you what I had to figure out on my own. But you can run a simulation of Maxwell's and see exactly. You can run a simulation of Maxwell's exactly like this and see exactly what happens. Then you can write maybe a simulation of Maxwell that allows for quantum effects, and you will see this quantum effect. Anyway, but we're not here to discuss quantum effects. We're assuming quantum effects as we know them to occur. That's what I understand. I'm not here to disagree. If I'm wrong, I'm wrong about understanding. I'm not disagreeing. I'm just assuming I'm assuming quantum mechanics. All of known quantum mechanics, I'm just assuming. I'm assuming the standard model. I'm assuming consensus physics I'm assuming YouTube physics. I'm assuming YouTube special relativity, general relativity, Newton, Galileo, and quantum mechanics, just as everybody on YouTube basically, take the average of the YouTubers. That's what I agree with, if such a thing exists. Okay, back to quantum gravity. All right, so we took a neutron and we just moved it. We moved it to here. That's all we did. Now notice as we're moving it, it's always sucking in space, right? So when it was here at an intermediate step, it was sucking in space onto here and to the right and from me and towards me, right? This is three-dimensional. You always have to remember everything is three-dimensional. Okay, but this is no different. So that's it, and that's when we enlarge it. But now let's make it tiny. So we took an electron and we just moved it a tiny bit. Let's say we moved it the amount of a photon, the minimal energy. We imparted on the neutron the most minimal energy that we could. Okay, so let me think what happens. So we're surrounded by the field, the unified field, and this field is flowing. It was flowing into here. So let's say we have a test particle. Let's put another neutron here. So this neutron was getting dragged. It was actually moving already towards the location of the first neutron. But now, okay, so now because the propagation of information through this field is at the speed of light, so it's going to take the speed of light. Let's say that the collapse of the fabric into the neutron is very slow. It's not very fast, so we don't have to account for relativistic effects. Of course, at a black hole, if this neutron is at the center, it is the center of the black hole. It is a black hole. It's a different story. But for now, let's assume no relativistic effects. So space is getting sucked in, and this guy is getting sucked in, but now the neutron quickly, not relativistically, but quickly got moved to here. So now the new motion is going to be towards the new neutron, but it's going to take time for this information to arrive. And this information, you can look at many, many test particles, and you can imagine a vector field, right? So this arrow is part of the vector field. You can imagine a complete vector field. So when we shock the vector field, when we move the neutron from here to here, we're causing a shock to the vector field. And just like before, it propagates as a single wave. These are not multiple wave fronts. This is a t equals 0, and this is t1 and t2. So we're getting a wave front. And just like before, as long as no one interacts with this three-dimensional, it's a sphere, it's a growing sphere. But this time, the way that it interacts with the environment, so this is the direction of the propagation of energy or information. This time it's a pressure wave. So the every bit of space, of the fabric of space, of the unified field, is moving to the left and to the right, and done. Just once to the left and once to the right, because we just did this one motion, and there is a shock traveling to the entire universe. This is going to travel through the entire universe, to the entire visible universe, so that every location at our field, every particle that makes up space itself, the very fabric of space, moves once to the left, once to the right, maybe once to the left, once to the right, and then goes back to its original location. So notice that this motion is first with the vector of propagation of information and then against. And this is called a gravitational wave. Whereas, remember, into is electric and to the right is magnetic. So it's just different, but it's the same fabric that is being shocked. The same shock. It's a very similar mechanism. So you can already guess what a graviton is going to be. Well, obviously, it's not going to be anything, but we are going to be able to detect it just like we can detect a photon. So let's say we're going to detect it with an actual particle. So let's say we have two neutrons at the two edges of the visible universe, one here, one on the other side of the 100 billion light years from here, on the other side of the visible universe, two neutrons. This gravitational wave, remember, it has just the minimal energy. It just has H energy. This is Planck energy, the smallest energy possible to impart to a particle in the standard, what do you call it? Oh, this is not even a standard particle. Neutron is not standard, okay, but whatever. So this is the minimal energy we can impart to any system, according to quantum mechanics, according to Planck. Very nice. So we have a neutron here and a neutron here. They can feel this gravitational wave. Only one of them, right? So all we expect to do is this vector to change from here to here. That is the detection. Only one of them is going to detect it, which is actually fascinating because, well, we know that it moved. So one of them is not going to notice that we moved the source of gravity, which is bizarre. But that is what comes out. Anyway, so only this neutron is going to change its motion. So before it was moving towards the original location, and now it's going to change to this direction, and that is a graviton detection. Congratulations to everyone. Nobel Prize for the detection of the graviton. By the way, no graviton for you, because a graviton is a quantum mechanical element from the standard model. It's a quantum mechanical particle, and that's it. Ta-da! That's what a graviton should be, according to my unified field theory. And that's it. That should basically conclude my presentation. Of course, I can talk forever about every little detail, and there's still so much to work out. I still don't know almost anything, but I know enough that I can put together the entire puzzle of all of known physics. I think that's it. I'm going to stop here. I'm going to take questions. We're going to have a separate lecture in which I'll take questions from our audience. Jimbo is waiting to ask questions, so we'll do a review with him, and then we'll take questions, or through the questions we'll do the review. All right. I hope everything is clear. If it's not, please ask questions. I hope you have enjoyed it. I think it's pretty simple. It's like very straightforward. What I like about it, of course, it's a mechanical. It's really quantum mechanics. Finally, it's a mechanical explanation of the quantum world. Well, it's incomplete, of course. It's just the beginning. Everyone is welcome to fix it. There's so much to rethink and think. There's so many details I didn't think through. But I think I'm giving you enough that you get to feel that this is in compliance with Einstein, with Newton, with Galileo, with Planck, with Higgs, with Schrodinger, Heisenberg. Everybody is accounted for. With Maxwell with quantum. I don't remember who did the Maxwell with quantum. Anyway, I think, and if I'm wrong, I'm wrong. Listen, if I made a mistake, please correct me. I know very little about this entire field. I'm new to it. I used to always hate quantum mechanics. I used to always be in denial. But now that I understand, it came to me as I was doing, as I was rethinking. I don't know why. I ended up from special relativity. I ended up developing or going back to Galileo and Newton, and then I developed my own general relativity, and then I felt I was fixing Einstein, but it didn't get fixed. It just was a little bit different with the solid fabric. I've seen other people talk about it. I know that it sounds like the ether. It's similar to the ether, but the ether is supposed to be ethereal. It's supposed to be very cloudy, and I don't like that because it sounds like you can move through the ether. But the fabric, this is a solid. This fabric is a solid. Nothing can move through it, because if you could violate the speed of light, and nothing can. We've seen nothing that can. So I think it's a solid or a very, very stiff liquid. Anyway, we'll continue in the next lecture. Thank you very much. Don't forget to like, subscribe, and share, and comment, and tell me whatever you think. Join our Discord, join our community. We have a very vibrant community, as you can see, with Jimbo here. All right, everyone. I'm going to stop here. See you next time. Bye bye.